Well, yeah, Dave asked me to say a couple words. There's about 9 of us or 10 of us here. And Barbara has a depth of experience, and she's pioneer in the industry. And I can't even begin to scratch the surface of what she's been involved with, projects and just as a collaborator of the community. But I'm excited today to hear from Barbara. What's your topic? What's your title?
Innovative grade controls for restoring an incised urban stream in a park in Raleigh, Millbrook Exchange Park.
Which is excellent, because that's a great platform for us to advance the voice of the ministry of good stewardship, connecting with people and people with the rivers. That's the only way we're going to get anywhere, because there's too many dirty diapers to change. So we need to change mindsets. And I love that she's out there and in the mix and changing minds and hearts. So without further ado, Barbara Dahl.
All right, I'm going to share my screen. You'll see yourself for a minute before I start the slideshow. All right, can everyone see the slides here?
Yep.
Okay, so a lot of the events people talk about when we go to some of the stream conferences, being sure that we share not just our successes, but some of the failures. And I think that's really important, because I think that's how we advance that. And it's been a strength of our stream restoration program here at the university that we don't try to hide any things we test and what the results are. We try to say, all right, these are the things that worked and these are the things that didn't. So that's kind of a big purpose of my project. I want to share a lot about lessons learned, so that if someone else starts going down the same road, you're going down it with open eyes. So as I mentioned, our project is in Raleigh, North Carolina. It was in a small stream in a city park, and we did an innovative kind of test project for research purposes, collaborating with the city. So the Millbrook Exchange Park was the site of our project, and we had about 800 and so feet of stream, plus a little tributary coming into it, located in the park. The watershed here, as you can see, is very small, 0.18 acres. Excuse me, approximately 180 acres, the watershed. And most of this was residential, and there was a portion of a golf course in the top of that. So here, if anybody knows Raleigh, here's our inner belt line 440. Here's the outer belt line. So we're out towards the outer belt line in North Raleigh. So this site had previously had an impoundment, likely a farm pond, and there was the embankment. And this pond, the dam breached in the 80s, and the sediment, the legacy sediment, and that kind of head cut worked through there and eroded that material out. And so what we were left with at the time we went to the site, when the city called us, was stream banks that were anywhere from 6 to 12 feet or more along the channel, eroding through that legacy sediment. But we also noticed on the right slide here a lot of sand and gravels that were moving through the system, kind of from some upstream bank erosion in the system. So the objectives and goals of our project were, we wanted to kind of really stop this active incision and erosion, hopefully try to improve floodplain connection, improve water quality if we could, but also to implement a project that would minimize cost and disturbance to the forest area there, which was a fairly young forest. I mean, it's not a 100-year-old forest, but it had a fairly mature forest in the system. So the project, this tributary drained into Perry Creek, which is a 303D listed stream. And the watershed, as you saw in the previous image, was pretty near developed, about 91%, but it was low density residential. So it only has about 11% impervious cover in this watershed. So here's the project reach that we decided to focus on through the park. And the first thing we did was set up monitoring of this stream. So we put a monitoring station at both the downstream end here and at the upstream end. And at these monitoring stations, we had a flume, an ISCO sampler, and a pressure transducer, and we measured discharge. We had the ISCO collect water samples in storm and base flow, and we looked at total solids as well as total suspended solids that were coming into the system and what was going out of the system. We built this pit sampler to trap bed load to kind of get an idea of the volume and the kind of particle size distribution of the material that was moving through the system. And then we also were measuring rainfall as well. Well, one of the types of restoration approaches we had considered for this site was a regenerative stormwater conveyance, where we would fill this gully of a stream with sand and mulch and kind of build some structures and stream habitats on top of that. However, we decided to look at different options for the project and consider cost. So we did a kind of a concept level design for 4 approaches. We did a grade control project where we would just try to intercept the sediment that was moving through the system, as well as we looked at 2 natural channel design approaches. Priority 1, where we'd reconnect to the floodplain that's there, or priority 2, we're going to excavate out a new floodplain, or we were considering the RSC channel. And what we saw with this is that the cost per linear foot was substantially less for doing the innovative grade control project. So this is why we decide to pursue this. We see the priority 1 and the RSC were very comparable in cost, and the priority 2 was quite a bit more, over double almost of the other medium priced approaches, because of all the excavation that would be required. And we know the priority 1 and 2 would have resulted in the loss of a lot of trees. So we decided to do this experimental grade control project. So what we did is we installed 11 grade control structures ranging from 2 to 6 foot in height. They were spaced about 40 to 60 foot apart, and they were intended to have about a foot or a little more of drop across these structures down the profile of this channel. So we can see the top of banks here. Here's where the right in this area is where the dam was, so you can see that high spot. And here's our structures, which they're very tall in portions of that channel where the stream had incised, to 10, 12 feet deep or more. Well, using our pit sampler, we developed a bed load. We took some measurements of bed load. We also took some measurements of suspended load related to discharge, because we were measuring that. And then in HEC-RAS, we looked at the equation fits and used the Van Ridgen equation to develop this bed load discharge relationship versus hydraulic radius. And then we looked at how much bed load would be discharged over time for various design storms, including the 1 year, the 2 year, and the 5 year storm, because we were looking at near term, what type of sediment deposition. So the area under each of these curves was summed to come up with a volume of sediment or a capacity that would be deposited in this channel theoretically, again, using the HEC-RAS and the Van Ridgen equations. Is someone trying to say something? I'm getting some kind of feedback here. I don't know if that's just from my microphone or anyway. maybe somebody has their mic on. Thank you. Okay. All right. So then we looked at the area that was behind each structure and summed that up volumetrically in a CAD using surfaces, and came up with that we needed 935 cubic yards, or 1,309 tons, 1,309 tons to be able to fill that channel up. And so when we looked at the amount of bed load for those storms, remember I said we kind of totaled the area under each of those bed load curves for the storms, we could figure out approximately how much sediment would deposit in the channel, again, using that Van Ridgen model, how many tons. So then we made some assumptions about what was going to occur in the next 5 years after we built the channel. And what we said is that we would get a 1-year storm, or the 100% return probability storm every year. We would get 2 of these 2-year storms, and we would get at least 1 5-year storm. And so what that led us to believe is that the channel would fill hopefully in 4 to 5, or maybe even 3 to 5 years, because we see by year 4 and 5 here, we're starting to get up around our 1,300, or we're exceeding our 935 cubic yards of material here. So we're at 1,150 by year 4. So somewhere in that kind of 3 to 5. So that made us happy. We thought that's a reasonable time to wait to fill this channel up. So immediately after completing construction, we then reinstituted our sampling protocol, again, of all the TS and TSS. And we also established 11 permanent cross sections, and we completed 13 surveys of that, along with a longitudinal profile to look at what type of aggradation was occurring to kind of document that. So looking at our post-construction monitoring, we have the total solids on the left and the total suspended sediment on the right. So if we look at pre-up and pre-down, we see there's not really much difference between the total solids and the system. Whereas when we looked at post-up, we see we had a reduction in what was coming into our site upstream, but we clearly see that we had a reduction in the total solids at the downstream station after we installed the RSC channel. So again, no change during that grade control period, and then we had post the grade controls, we have a reduction. Same thing we see with the TSS. And actually we see a little bit different, because in the pre-grade control, we have a bit of an increase from the upstream station to downstream. So that was some stream bank erosion, we believe, happening in that channel, active erosion. If we look at the post-grade control, the upstream to downstream, we see a pretty significant shift in that TSS, a reduction of that. We also looked at the loading that passed through the system and compared the upstream load to what was exported out of the system. So here's our post-grade control treatment period. We have 12 storms before and 20 after. And we can see in all storms before the grade controls were installed, we were always exporting some amount of sediment out of this. And we have the kind of rainfall amounts for these various storms. And you can see bigger storms typically exporting more material than some of the smaller storms. Whereas post the grade control installation, out of the 20 storms, we see that 4 of them exported, 1 of them only a tiny bit, but a few of them did export some, but most storms were resulting in a net capture of sediment in the system. So most of them were a reduction. The upstream load exceeded what was exported out of the system. So that said, yes, we were capturing some of the sediment moving through the system. Well, looking at our 11 cross sections, When we looked at the upstream cross section, we saw over time quite a bit of aggradation. We were capturing material in this. We were getting that desired deposition that we were hoping for. However, in the middle of the stream, we saw very little aggradation in the system. So in other words, this kind of tank is filling up the first cells, but that material hadn't reached the bottom cells, is what we were assuming was happening here. However, at the bottom end, we saw something very concerning where we were not only not aggrading, we were eroding significantly below a lot of the structures, quite a bit of erosion in, of 2 and 3 feet below these structures, which was quite concerning. If we look at the profile, we can see the black hatched areas are where we're getting deposition, but we see below each of these structures quite a bit of erosion, especially, in the lower end of this project, because it is steeper at the bottom end. We had the deepest erosion levels in that. What we showed is in our kind of then taking the cross sections and the profile, we estimated the volume of material that had been aggraded, which was about 42 tons of sediment aggraded in a year over this monitoring period. And the monitoring period was about a little over a year and a half. It went from spring of 2019 to the end of the year in 2020. So we estimated at this point that was going to take 21 years to fill our channel. So that didn't make us very happy and was quite concerning, especially considering we saw these really extreme erosion occurring downstream of the structures. So just to show you some pictures of this, we see here's one of the structures. The city did want these PVC low drains in case they were holding too much water during summer and we're getting mosquitoes. They wanted a way to drain it. We never ended up using these, but we can see some of the aggradation that occurred in that channel here on the left as well as on the right, where it's almost kind of forming a series of step and small riffles. This is actually the back side of the next structure. But what we also saw is we saw that in a lot of areas we were not aggrading as fast as anticipated. And this severe erosion below the structures resulted in some undermining of these structures. I will mention that the contractor who built these structures was an on-call city contractor that had never done anything like this. They really didn't have the proper equipment, and they ended up requesting smaller rock be installed because they didn't have the right kind of track hoe with hydraulic some, and so how they were moving the rocks in was not the best situation. So the structures were not well built, and we saw this cutting around of the structures as well as the undermining. So this was more than concerning. This was pretty frightening to us with this undermining of the structures. So starting to realize maybe this wasn't the best idea, we decided to look at some more detailed modeling because, look, our HEC-RAS 1D model with all our sediment transport analysis, it showed us, hey, this was going to be the situation. So we said, well, let's maybe try some more detailed modeling. So we decided to look at some HEC-RAS 2D modeling. Well, if we look at the 1D model, how that's built is we have the long profile, the elevations down the channel, and then we had inserted these survey cross sections of that channel. And then the 1D then just continues each cross section form all the way down the channel. Also, it assumes a uniform velocity across the entire cross section that's in a perpendicular movement, just across that channel. It does not allow for any variability across the cross section in the channel. So what we did with the 2D, how that was different is you build a mesh, and the mesh we built was 1 foot. And so if we look at that mesh, that gives us a lot more detail, and this allows for different velocities across each cell. It's not the same average velocity across the cross section. However, in each cell, the velocity is uniform from top to bottom or vertically in that. And with the 1 foot cells, we also made even a finer mesh at each structure because this would allow us to better define the structures. So then we simulated discharges for our watershed using hydroflow. So here's the 1 year through the 100-year storm, what the discharge would be. And then we looked at the flows we measured with our monitoring stations and what magnitude that had occurred. So we had 10 storms that had occurred in our little over a 1.5 year period. 5 of those storms were about a 1 year discharge. We had 3 storms between the 1 and 2 years. We had 1 storm at the 2-year level. We had 1 storm between a 2 and 5 year magnitude, and then we did not have any storms that had gotten to the 5 year or above in that monitoring period. So here's our mesh for the 2D model. And as I said, we got more detailed at 0.25 foot the mesh at these structures in order to really better characterize the velocity differentials or variation across that structure. And if we look at the results of that, we look at that 1 year storm, that was about 30 CFS. We saw these kind of high levels of velocity kind of reaching up into the 5 and 6 foot per second above, which starts to become concerning in one of these channels, and really more extensive high velocity in the lower end where this channel is steeper. We saw that same thing in the 2 year, and these levels of velocity even, getting worse and more expansive in the region. And again, the lower reach of this channel is the steeper portion of this stream. And then in the 5 year, quite a bit of, concerning velocities as well. If we look at a velocity profile moving from structure 1 down to structure 11, so moving upstream to downstream, we have each return interval storm. We can see at the lower end about structure 7 or 8 and lower that we're frequently getting above 5 to 6 foot per second velocity, and about structure 9, very high velocities over, up around over 10 foot per second. So this is quite concerning. So even though the 2D hydraulic models are much better than the 1D, and it gives a good idea of kind of the velocity in the channel, it still assumes a constant velocity from top to bottom of each of these grid cells. So it's not really allowing for kind of vertical variation of the velocity. It's constant with depth. So it's really not suited to these kind of large elevation changes where you're going to have energy loss and turbulence at these structures. And so Dr. Kirky Fox, who works here, who had done the 2D modeling, he also built a flow 3D hydro model for just one structure to kind of say what's going on in this structure. Let's really look at the situation. So he again built a mesh with this to really define the structure. And looking at the 2 year storm, he did a kind of synthetic flow. This is kind of compressing a storm into a short timeline. I'm going to play a video here that hopefully works, but this is to kind of show you the recirculation and hydraulics of this. If you had a true kind of flow event, this simulation would take 2 hours. So this is a very short simulation. Whoop, let's try to click on that. All right, so what we see happening is at the start, before we have backwater conditions, I'm going to play that again when it gets done here with this round. We can see very high velocities in that deep scour that took place right below the structure. And then the velocities do tend to focus more at the top of the channel, although we still have on the bed some high velocities that are hitting that. And I'll show that one more time. That's pretty cool, isn't it? That he built. So that's what's happening. And this, even with the backwater, we do see higher kind of velocities isolated to the bottom. So that's why we're not going to get kind of filling of the entire channel that we have here. Okay, And the grade control structures, another issue that we saw was they did not adequately connect the channel to the floodplain. And in fact, in 25-year flow event modeled, we saw a lot of the flow was still confined in the channel, and this resulted in very high velocity and shear. Some of this was due to the design, but also some of it was because some of the structures were not built in the locations or at the elevation that they were designed. And we ended up with several structures with just a really large vertical distance between the structure and the floodplain. So we look at the 25-year storm, we see some areas of the channel that were getting some overbank flow into the floodplain, but lots of areas where we're not. And we see these, that's what, again, where we have these very high velocities where a steep slope at the bottom end. With the 100-year storm, we do see that we're getting out of bank quite a bit at the top, but again, at the bottom where we have the steeper slope and a lot of high velocity, really minimal overbank flow. So this was a big part of our concern for the project. This is a photo. I went out there this weekend because the city's supposed to make a kind of retrofit to our experimental design. That's being done by another consultant. So we do see that the stream, we saw really no real change in the aggradation. Of course, we didn't resurvey the cross sections, but just visually walking through and compared to the last couple surveys, we saw no more real significant aggradation. And of course, these structures that are failing, they're only going to get worse. So this is the probably most important slide that I'm going to show you here is the recommendations and the lessons learned from this project. Is that really, if you kind of decide to go into this concept of capturing the sediment, how you build your structures and evaluate them, I would strongly consider using 2-dimensional and 3-dimensional models. So you're getting a more detailed picture of how the grade controls are going to affect the velocity profiles, what kind of shear stress and velocity gradients you're going to see. Because these 2D and 3D models that we did then really seem to explain what happened. And
Hey Barbara, I can't really hear you. Can others hear you?
Yeah, I'm getting. I'm tracking your you're pointing, but it's like some max headroom mouse kind of sounding squeak. Let's hear you try it. Yeah, you're squeaking, like not sounding normal. No.
It's like the cat video.
Yeah, it's going meow, meow, meow. I wish you could hear this. Like we can't really make out words.
take these out. All right.
That's
Is this better? Can you hear me?
yeah.
Oh.
You're good.
Yes.
All right, talk one more time. I make sure I can hear you.
Yes, we can hear you now.
Okay. All right. So did you catch the part about the 2D and 3D models, or should I say some of that again?
No, we caught that first bullet. You were
Okay.
the second bullet. You started to squeak out.
All right. So then really, a big fault of the project on our part was to not have adequate floodplain connection. So this would have, minimized some of the velocity in the bigger storms and some of the recirculation. Another thought would be to consider those alternate design approaches where maybe, the priority 2 or 3 combination could have been done, or the RSC channel, because adding that media would have, kind of collapsing some of the banks, putting some media may have provided a lot better scenario for the stream. And I think a very big lesson learned was the contractor that was used in this. And in fact, that switch that they made to the smaller rock was really detrimental to the project. Unfortunately, I wasn't there when that decision was made, because I would have recommended it. So
Just went max headroom on us again.
what's that?
You just, we can hear you now. For a moment, it was max headroom again, but use experienced contractors where you were, and it sounded like you were open for questions.
I'm not sure. What's that mean, max headroom?
Oh, don't you remember back in the 80s, Max had headroom? It was a
Yeah. Okay.
digital
yeah.
personality. Yeah.
Right. Okay.
Sorry, I'm old.
Yeah, I don't know why it's doing that, because usually our interweb here at the university is pretty good. For the hardwired system.
So did you open the floor for questions, or was
Yes, I did. So you didn't hear that. Yeah, so that's all
Yes.
I have for slides and presentation. So yeah, I'm happy to entertain. Hopefully I can
I wanted to start because I was excited. This is a great presentation. Thank you for sharing this. I love the experimental nature, and I almost think it's almost serendipitous that the contractor and the work didn't withstand because there was a lot learned afterward. So I had just an easy question with the original design. I know you weren't changing the alignment. There was a lot of light touch. So what was the design mindset? Like a B little C type channel? I noticed connections at the bottom.
Oh, are you mean for the design comparisons?
Yeah, no, the original design, you sized those weirs and those sections, and
Yeah, we made absolutely no changes to the existing channel configuration. It was literally just put the structures in this channel. So and that's one of the things we've seen, is that with the flows coming up and sitting with the structures where the banks were very vertical, we actually see some bank collapse. So remember, I showed the 20 post storms where a few of those had exported material, even though most of them, and I think that's because of periodically we're getting the slumping of the banks that is raising that volume of exported material.
Well, let's I have a few things in the chat box. No questions. Can I open that floor? Can anyone throw some questions out to Barbara about this project or anything else?
Yeah, I've got one.
Thanks, man.
Barbara, so what I've noticed more and more is that we are seeing clients who are opposed to bringing in large rock material, especially kind of in these systems that are currently, sand bedded. I'm wondering if you all have either performed an experiment like this using kind of beaver dam analogs in the same configuration, and or if you think that something like that would be kind of a nice alternative here to be the light touch approach, but not bringing in, a bunch of rock from external sources.
I think it could be. I think the banks, I agree. I think that would be a good experiment to try, but I think if not done right, it could have some of the same issues we saw here, because you're not going to fill the whole thing with structure. You're going to have a spacing, and maybe the spacing would need to be evaluated on this. And also, you know, with this complete vertical drop off the downstream end, we thought about trying to repair this and building like more of a ramp coming off this bottom end so that it would hopefully
Cascade.
maybe, yeah, like a cascade coming off of it. And we thought about that. But because the structures, the rock was so small and how it was done, we felt like, you know, this needs a complete rework, that the issue with the structures, but also I think some bank grading and maybe cutting a floodplain bench up on the top of this would have to be done, whether, no matter what the structures, whether it's wood and configured like analogs. I think you would have to do a little grading in the corridor to if you're not going to put something to fill this channel, that the hydraulics and that kind of raising up and saturating banks, and then the flow comes down at times, and the banks collapsing would have to be addressed. Does that make sense?
Absolutely, and I tend to completely agree. I mean, that's anytime I do this kind of work, I try my best to reconnect floodplain to the maximum amount. So yeah, I completely agree. And I guess quick follow-up question, is there have you all written any kind of report or anything summarizing these results, and or would that report / this presentation be available for us to kind of share with potential clients to explain why we're doing what we're doing?
Sure, yeah, I can share the PowerPoint, and we have first, we have a basis for design. We have 3 kind of small reports. One's the basis for design of the original. We have the one that compares the different approaches. And then we have this 2D, 3D modeling report. And I'm happy to share those. I don't know the best way to, if I just email them to Dave or to
Maybe
somebody.
get with Paula.
Paula, okay, I'll send these all 4 items to Paula, and then if she wants to post them somewhere, if y'all have on the website or whatever, that is fine.
That would be great. Thank you so much.
Questions?
Anybody else with questions?
Man, I love that you guys worked into the 3D model to bring the visibility that's not there on the 2D. You know, we all of us on this call probably have worked in municipalities and working with their modeling, floodplain folks, and the low bid and all of those types of problems, that challenges that we confront that aren't, you know, but what I really was interested in is downstream. It looked like some of the retrofitting ideas included a different spacing. And since this channel, you know, since you lack the ability to get it out of the bank for the dominant process in the channel forming flows, it behaves like an AB channel with floodplain relief, and as such, you know, maybe a higher a lower pool to pool spacing and some armoring, and those are solutions in an urban environment. And you know, while priority, you know, 1 or 2, or you know, these other more surgical treatments, or maybe less surgical, more overhaul treatments might bring us
that term, surgical.
Yeah, this is surgical.
Coming in and just operate in the spot.
Yeah, while some of those treatments might bring a different level of assurance, you know, we have to find, you know, cheaper, better ways to restore function and let the stream heal itself. And I think this is really an innovative, a good, you know, it took some fighting to move these things forward, I'm sure.
Yeah, and so I think it's, you know, really good that we do use our, you know, lessons learned here, and that's why I'm happy to share it, because I don't want, you know, because we went into it maybe not enough information and kind of a perfect storm for things not to work out. And I think people can use this and expand on it and kind of the lessons and try to tackle, you know, put some more engineering minds on it and try to tackle the issues, and maybe this could be refined into an approach that
does those objectives that we originally, those were good objectives we started out with, to keep costs down and to, you know, kind of try to stop some of this erosion and not destroy this whole forest and a park, which is a big issue in the kind of Maryland area when we're getting hit hard, but that, you know, the RSC is pretty expensive approach. But anyway, I think, you know, the experimenting with the other structures such as the wood and the spacing, as you mentioned, Josh, that maybe pull-to-pull spacings need to be shorter than what this allowed for.
How about any more questions? I know we're running out of time and Monday's here. We have contact information and a little profile available on the River Shared website. If wherever you got the link to this call, you should also have a link to the website. And if you don't, just look up rivershared.org and surf around and let us know what you think. And if you need anything, we'd love to share and serve more. And Barbara, thank you for sharing. There's thousands of miles of urban streams that could benefit from this one experiment. And so, yeah, I can't wait to see what you guys do next. Yes, so thank you very much. And everybody have a great day. Oh, wait.
Thank you.
Thank you.
Thank you, Barbara.
Thank you, Barbara. Okay, bye, Josh.